MAP4C 6.7 Applications of Exponential Equations. Previously, we learned about the exponential equation in the form y is equal to ab to the power x, where a is the initial value and b is the growth or decay factor. So whether this function increases or decreases depends on the decay factor, b, in this equation. When you multiply a number by 1, you get that value back. But as soon as that factor exceeds the value of 1, the image gets larger, or the product gets larger. And that's why we see exponential growth when the value of b is greater than 1. Remember that b to the power x is an abbreviation for repeated multiplication. Therefore, an example, y is equal to 2 to the power x, looks like the following. We're seeing it double. Similarly, with exponential decay, when we multiply by a value that's less than 1, the image is reduced, or the product is smaller than the original value. So we see exponential decay. In both cases, we see a horizontal asymptote on the x-axis. But let's focus on this b value, the growth factor or decay factor. Being between the values of 0 and 1 will cause a reduction in the image. Next, using a table of values, the population of Ontario was 9.4 million in 1985 and has been growing at an annual rate of 1.25%. This situation can be modeled by the equation p is equal to 9.4 times 1.0125 to the power t, where p million represents the population t years after 1985. In which year did Ontario's population first exceed 10 million? So first of all, let's investigate this equation. 9.4 is representing the initial value, and this is expressed in millions. This factor, 1.0125, is an increase by 1.25%. So when we multiply by 1, the first component, we get the original value back. But this additional component, 0.0125, is how we would increase a value by 1.25%. And if this is occurring every single year, we would just multiply by this value each year. And that's accomplished using this exponent, this power. So to solve this problem, we're given the equation, but we're interested in when Ontario's population first exceeded 10 million. So we're going to let p, which is our output in this equation, equal 10. So one method to solve this exponential equation is to use a table of values. Recall that this is an exponential equation because the variable t is in the exponent, and we can't use our traditional opposite operations in order to isolate the variable. So looking at the values, what we could do is substitute in for different values of x, observe what we get for the value y, just by substitution for the value t in this equation. We can see looking down this list that the population first exceeds 10 million at x is equal to 5, which corresponds to t for our equation. So our approximate solution is 5. Remember that mathematical models approximate things like population growth, but there's many external factors which would contribute to population growth. So it's good for an overall guess, not precise values. Another technique for solving exponential equations would be using a graph. A website like desmos.com could be used to graph both the function y is equal to 9.4 times 1.0125 to the exponent x, and y is equal to 10. So it's hard to see in this graph because a growth rate of 1.25% is very gradual. This is actually an exponential curve, even though we can't see it within the graphing window. So this is the exponential curve. This horizontal line represents our target of interest here. We have a population at 10 million for this horizontal line, and we're interested in when does our function exceed this value. And we can scroll with our cursor to the point of intersection, and it's approximately 4.981. So that would be, as defined in our question, the number of years after 1985. So, quantities that grow and decay exponentially increase or decrease at a constant percent rate. The doubling time and half-life of a quantity are used as a standard to describe growth and decay. So let's investigate the formulas for both doubling time and half-life. The doubling time of a quantity is how long it takes for an amount to double. So A null, or A subscript 0, is the initial amount, what we start with. The base is 2 because we're talking about how long it takes for something to double. What is new in this section is this rational exponent where t represents time, but the denominator represents the period. How long does it take to double? So that's why it's the variable d in this equation. So this is an exponential function. It's just that we have introduced the idea of doubling and half-life with the concept of a period, which will become helpful in future chapters. Next, the half-life of a quantity is how long it takes for half of the amount to remain. So we still have some components that are the same, such as the initial value. The growth rate is a half. Our variable t represents time, and the denominator of the rational exponent is h, which stands for the half-life of the quantity. So we'll see some application questions. Solving an application of doubling time. The doubling time of an investment is 8 years. If $1,000 is invested today, then how many years will it take to become $1,500? Determine the time to the nearest tenth of a year. So we're going to apply the guess method for gathering our information. Starting off with the given information, we're told that the investment will be 8 years, the doubling time is 8 years. The initial value is $1,000, which we're putting in at the beginning, and the amount that we want to accumulate is $1,500. So this is an exponential function, and our output is 1,500. How long does it need to be invested? We don't know the time, so we've got our given information. Our unknown value is the time. Next, we need to look at our equation, which equation includes all of these variables, and that is our doubling time formula, where our amount we want to get at the end is 1,500. We initially put in $1,000, where the amount is doubling every 8 years, and we're trying to solve for this variable t within this equation. So we can come up with a table of values, and using systematic trial, we can guess values within the neighborhood. And once we find a value on the left and right hand side, which is less than, and then one value that exceeds, then we can use the midpoint. So we find that the value for t years is between 4 and 5 years, because when we substitute into this equation, the solution is somewhere between approximately 1,400 and less than this value here. So we'll use the midpoint by adding the two endpoints together and dividing by 2. So the midpoint is 4.5. Once we substitute into our equation and evaluate, we'll make a decision whether we start going up by tenths or down by tenths. Since we are below the desired value of 1,500, we'll go up by tenths. So 4.6, we're still not there, and at 4.7, we've exceeded our desired value. Then what we need to do is look at our endpoints. We are asked to round to the nearest tenth, and the place name to the right-hand side of the decimal is the tenths place. This value is closer to 1,500 at 4.7 compared to 4.6. So we will say the amount will be 1,500 in approximately 4.7 years. Next, solving an application involving half-life. Caffeine has a half-life of approximately 5 hours. Suppose you drink a cup of coffee that contains 200 milligrams of caffeine. How long will it take until there is less than 10 milligrams of caffeine left in your bloodstream? Determine the time to the nearest hour. So again, applying the guess method, the given information, caffeine has a half-life of 5 hours, so that is the variable h, 5 hours. Initially, you have 200 milligrams from your cup of coffee. And how long does it take until there is less than 10 milligrams of caffeine left in your bloodstream, that means we're interested in when is the amount 10 milligrams. How much time does this take is unknown. So we have our given, our unknown. Next, which equation includes all of these variables? And that is the half-life formula. So given, unknown, equation. Next, we substitute in our given values, and we can see that this is an exponential equation because only t in the exponent is unknown. So the next thing that we need to do is solve, and the way that we can accomplish this, again, is with systematic trial. I first guessed 24 hours and saw the result, and I was at 7.18 milligrams. Now, if you can recall, this is a value of b that is between 0 and 1, so this is a strictly decreasing function, which means I would have to look earlier to see larger values. So I started moving backwards by 1 hour, and it was still less than 10 milligrams. Back to 22 hours, still less than 10 milligrams, but at 21 hours, the approximate level of caffeine in the bloodstream is 10.88 milligrams. So after 22 days, there's less than 10 milligrams of caffeine left in your bloodstream.